So here's a graph, and the question is very simple. Does this graph contain a triangle, and if so, how many? By a triangle, like a triangle means three vertices where every pair is connected by an edge. For example, you can see a triangle over here. So a triangle formed by this vertex, this vertex, this vertex, and these edges, for instance. Of course, um, one can, like, for small graphs, you can probably just look at the picture and find one and count the triangles inside this inside this graph. However, if the graph has like thousands of vertices, we need an algorithm, and we not only need an algorithm, we need an algorithm that runs kind of not naively, because the naive way of doing things is like to run over all the vertices, like to consider all triplets, to like combine these, so for example, there are and choose three many triplets. So if we have n vertices, then there are that many triplets, and that's approximately like for large n, this is of order n cubed. So we don't want to do this naively. We want kind of a faster method of doing things. So let's see how we can improve this amount of computation that we need using linear algebra. Okay, so here's what we're gonna do. So let's enumerate the vertices by 1 to up to n. So if we call the vertices 1, 2, etc. So if we have a graph, so let's start like this. So if we have a graph, let's say a graph with vertices 1, 2, dot, dot, up to n. We may define a matrix that kind of represents this graph. And here's how we can do it. So let's define a matrix A to be formed of entries Aij, where Aij is defined as follows. So we're going to define Aij to be 1 if there's an edge between I and j. So if I is not equal to j and ij is an edge, meaning these are connected. So just so that we're on the same page, what is it that we're trying to count? So we're trying to count the number of such shapes inside a graph. And notice that the observation here is that of course we're counting it's going to be formed from 3 vertices, and these vertices must be connected. In other words, there must be an edge between every 2 vertices. Okay, so these are the objects we're trying to count inside this graph. So let's try to kind of formulate this problem in terms of linear algebra and see how to do things. So let's define Aij to be 1 if there's an edge between the element I, or the vertex I, and the vertex j, for example. And then we define it Aij to be 0 otherwise. So now we have a matrix that kind of represents this graph. Okay, so a 1 means there's an edge, and a 0 means there's no edge. Since this graph is undirected, in other words, since it doesn't matter which direction we go on an edge, the matrix is going to be symmetric, and you can see, because if there's an edge between I and j, then of course there's an edge between j and I. Okay, so this matrix is going to be symmetric, and also it's going to have the diagonal is going to be zeros. It's going to be a 0 diagonal. Okay, so now comes the important move, I guess. So here's what we're gonna do. So let's look at the matrix B defined as A squared. So this matrix, before I speak about this matrix, let me say that this matrix A has a name, and it's called the adjacency matrix. So let me just write that for you. So this is called the adjacency matrix. Okay, so let's look at the square of this matrix, and and we're gonna see that by looking at the square of this matrix A, we'll be able to solve the problem. In other words, we'll be able to know the number of vertices, the number of triangles in a general graph formed of n vertices like this, okay? So remember, these are the vertices. All right, so let's see how to do that. So, the observation is that the entries of A squared have meaning, right? So it may look like a random operation that we're doing here. However, once we look at the entries of this matrix, we will see that they have meaning. So let's look at these entries. So by definition, this is what? This is the matrix Aij multiplied by the matrix Aij. So if we want the ijth entry of the matrix B, so if we call that Bij, this is gonna be the entry of the matrix, the ijth entry of the matrix A squared. And of course, by elementary linear algebra, this is Aik, Akj, as k runs between 1 and n. Okay, so now let's try to understand the meaning of this entry. What does it say? So if we look at every term of these, so the observation here, let's observe that every entry, like if we look at an entry of this form, a summand, so if we look at the general summand, Aik, Akj, so what is this? So this is gonna be 1 if and only if Aik is 1 and Akj is 1, right? Because of the very definition of Aij, I guess. And this is gonna be 1 if and only if Ik is an edge and Kj is an edge. Okay, so far so good. So this product is equal to 1 exactly when both of the edges exist, okay? So what we can say is that the this equals 1 if and only if we have these vertices I and j, and they're both connected to the vertex k. So this is the observation. This is the meaning of this entry equaling 1, or this summand equal 1. So the meaning of Bij is thus the following. The Bij can be thought of as the number of common neighbors of I and j. So I and j, they're gonna have neighbors, meaning they're gonna have some vertices that they're connected to by an edge. And if we look at the neighbors that are common to I and j, this is what the Bij is gonna count, okay? So the key idea is that squaring the adjacency matrix counts common neighbors. And this is exactly what we need for triangles, because a triangle is just like an edge together with a common neighbor. So let me explain. So if I and j are connected, if I and j are two vertices and they're connected, meaning if we know that Aij is equal to 1, so if we know this, then triangles are formed by by a common neighbor k. So if k is a common neighbor, is some common neighbor of I and j, then this is how we form a triangle. So triangles are formed in this way and only in this way, okay? So the condition we're looking for is thus, we'd like I and j to be connected, and we'd like k to be a neighbor. We'd like to have some neighbors of some common neighbors of I and j. So we'd like to have this one. And it's not so hard to see now that this is a triangle detector, quote unquote. Okay, so this idea can be used to count triangles because we can now do the following. We can simply sum aij times bij, and this will give us the overall count. However, we would have overcounted because every triangle has exactly 3 edges, so every triangle gets counted 3 times. So what we need to do, so if we sum here over ij between 1 and n, what we have thus is that if we divide by 3, this number by 3, we get the number of triangles. So this will give us the number of triangles in G, in the graph G. Okay, so this is a formula. This is a formula that we can use, and you may wonder, why is this useful? Well, the reason this is useful is that so let's recall why we went over all of this. Well, we already knew an algorithm, which is the naive algorithm, which is the algorithm of going over every triplet inside the graph and checking if they form a triangle, but that was of order n-cubed operation. So the advantage of linear algebra here is that notice that the only expensive operation that we need is this one, and this can be done in cheaper than order n-cubed operations. We can do it in there's an algorithm, for example, due to Strassen, that says such an operation can be done in order of n to the power 2.807, and that's a very big improvement if you know a bit about computational complexity. So for a huge n, this is a huge improvement in computational complexity. So linear algebra, quite surprisingly, give us a way of improving the count, the computational complexity for counting problems such as this one. And of course, there's no reason to stop at triangles. Of course, you can do it for polygons in general. Okay, so before we wrap up this video, let's quickly look at an example. So if we look at this simple graph, and not to say that we need an algorithm to do this, but just to illustrate that the algorithm we introduced works, if you look at this graph, you see that it has 2 triangles. It has this one, it has this triangle, so this is 1 and this is 2. So we have 2 triangles here, and let's see if the algorithm works. So what are the edges here? The edges are between 1, 2, 1 and 2, 1 and 3, 2 and 3, 2 and 4, 3 and 4, and 4 and 5. So these are the edges that we have, okay? And then if we compute the adjacency matrix and its square, this means that in these entries we're gonna have 1s and then the matrix is going to be symmetric, and elsewhere we're going to have zeros. So for forming this matrix A, we have this adjacency matrix, and its square, you can compute it, and it's something like this. Then the observation is that if we go ahead and use a formula, which is the sum of Aij, Bij, we see that this is going to be 1 plus 1 plus 2 plus 1 plus 1 plus 0. And this is exactly 6, and thus this is, if we divide by 3, this is exactly 2, which is the number of triangles that we observed.